Welcome again to another episode of Standing on the Shoulder of Giants, and this week we'll be looking at exoplanet discoveries. Tatooine, Vulcan, Krypton. Imagining planets in distant solar systems has long been a favourite pastime of science fiction writers. For decades these planets were just a tantalising possibility, but these types of planets, also known as extrasolar planets or exoplanets for short, became a reality in 1992 with the first confirmed observations of a planet orbiting another star. Today, astronomers can count more than 5,000 worlds orbiting stars light years from our own Sun, and that number is increasing every day. From this research, immense and detailed new subfields of astronomy have been born, focusing on a large-scale census of exoplanets and detailed studies of this rich variety of newly discovered distant worlds. The idea of planets around other stars has been around for well over a century, but it's always been accompanied by a crucial and puzzling question: how could we possibly find them? In our own solar system, a planet like Jupiter or even a dwarf planet like Pluto can be spotted by observing the sunlight that they reflect. But exoplanets are much too small and dim and far away for such a method to be effective. So how can we know that there's a planet around another star? I'd like you to think for a moment about what we've learned in these programs so far. Try to imagine how we might use some of the observing tricks and techniques that we've covered to search for exoplanets. Take a few moments, scribble down a few ideas, and let's see if your ideas hit on some of the tricks astronomers might use to search for exoplanets. To begin, you might not want to give up on capturing an image of an exoplanet just yet. Remember, we normally can't see the faint little stars around the Sun in the blinding light of day, but Arthur Eddington managed it just fine in 1919, during a solar eclipse. What if we could do the same with another star, one with small faint planets around it? What if we could simulate an eclipse, blocking out the light of the star and taking a good close look at its surroundings with a powerful telescope to see if there are any exoplanets there? Astronomers do this all the time, using an instrument called a coronagraph that places a circular or a bar-shaped mask in the centre of the telescope's field of view. If the name coronagraph sounds a bit familiar, there's a reason. The first coronagraphs were used at solar observatories to study our Sun's own corona. Now we can equip our largest and most powerful telescopes with coronagraphs and use them to study other stars. Blocking the light from these stars acts like blocking your eyes from the bright light, making it easier to see the dimmer surroundings. We use coronagraphs to study the winds and mass shed from stars, map the surrounding dust and spot small binary companions. If we think of planets as simply very small and dim binary companions, this sounds like a great way to search for them. The downside is that this method of trying to capture a direct image of a planet is incredibly difficult. It assumes that the planets are big enough and close enough to their host to reflect enough light to detect them, but not close enough that they're covered under the mask of the coronagraph. Coronagraphic observations are also time-consuming and can only be carried out by focusing on one star at a time, making it an inefficient method of carrying out any kind of large-scale exoplanet search. Ideally, we'd like a method of finding exoplanets that can search many stars at once. You might have also thought of using something like a light curve to detect exoplanets. What if a star is being orbited by a planet that passes directly in front of it, blocking some of its light? This should work very much like Pluto occulting a background star, except the star will simply get dimmer instead of disappearing entirely. If we can monitor the light curves of stars very carefully, we should detect a nice clear drop when a planet passes in front of them, and that drop should repeat regularly every time the planet completes another orbit. Astronomers have had great success with this method in the past while studying stellar binaries, and it certainly sounds like it would work very well for planets. But this idea depends on the orientation of the planet's orbit. It only works if the planet is passing in front of the star. What if, from our perspective, the system is tilted, with the planet appearing to move around the periphery of the star rather than passing directly in front of it? Or what if the planet is simply too small to block enough light for us to notice? Back to standing on the shoulder of giants and discovering exoplanets. Let's try another idea. We have also talked about gravity in these programs, so another possibility could be to search for the telltale tug of a planet's gravity on its host star. At first this might sound like an impossibly small effect, but it can be measured by closely monitoring the motion of the star. To imagine how this works, let's picture two objects orbiting one another. One of the key principles of physics tells us that since both of these objects have mass, and as a result gravity, one isn't really going around the other. Instead, both of these objects are orbiting around some point between the two of them, known as their centre of mass. This means that both objects are in fact moving. The centre of mass will be much closer to the more massive object, so it may only be moving a very little bit, but the motion is still there. Remember what we've learned about redshift. When we talked about the observations of stars and galaxies, we've learned that an object moving away from us will have the wavelength of its light stretched, making it appear redder to us, while an object moving towards us will have the wavelength of its light shortened, making it appear bluer. We see this very clearly if we collect the spectrum of the object. In these data, the telltale stripes of atoms like hydrogen and helium will appear noticeably redder or bluer. Now imagine applying these concepts to a star with a planet around it. If that star has a planet, the two objects will orbit around a common centre of mass, and the star will periodically move towards or away from us. If we repeatedly take the spectrum of the star, we'll see the lines of its spectrum shift back and forth as it moves towards and away from us, tugged by the planet and orbiting that centre of mass. For both this method and the light curve method, we can also use more sophisticated models to determine whether the timing of the orbits or the motions of the star is best fit by one planet or by multiple planets, with a whole planetary system of objects influencing each other's gravity. Maybe you thought of using gravity to search for planets, but you got even more creative. What about gravitational lensing? That consequence of general relativity where we see massive objects warping space-time and bending the path that light takes as a result. Shouldn't the mass of a planet have a lensing effect? Shouldn't the mass of a planet have a lensing effect, even just a tiny one, on its surroundings? It turns out that the answer is yes, though maybe not in the way you might imagine. Planets are far too small to measurably lens stars by themselves. However, their host stars could lens other background stars, and we know that how the light of these background stars is lensed depends strongly on the mass of the object or system doing the lensing. If the lensing effect is off, even a little from what we'd expect based on the mass of the star, it tells us that there's more mass present and that this mass could be in the form of a planet. This method is difficult, but it could potentially work really well, capable of picking up extremely small amounts of excess mass from planets around a star. Think about all of these different methods again. Using a coronagraph to directly observe exoplanets, searching for planets blocking light in a star's light curve, spotting the redshift effects of a planet's gravity on its host's motion, or relying on a gravitational lens. Which of these methods would you want to use to search for an exoplanet? And which one do you think might have succeeded first? Astronomers today have used all of these methods to find exoplanets, although some are more efficient than others. The first confirmed detection of an exoplanet used something entirely different, however, a pulsar. On the night of February the 9th, 1990, astronomer Alex Wolfshan decided he would go looking for a few pulsars. He was observing at the Arecibo Observatory in Puerto Rico, but because of a technical glitch he couldn't pursue his research. Arecibo was an immense radio telescope with an unusual design. The 1,000-foot dish was built into the ground, nestled in the natural depression of a sinkhole. The dish itself couldn't be moved, but the telescope can still be pointed at different parts of the sky by moving a receiver suspended 500 feet above the dish. Unfortunately, on Wolfshan's night at the telescope, that receiver was malfunctioning and couldn't be moved. Unable to point to different parts of the sky, the telescope could only look straight up. Still, unwilling to waste telescope time, Wolfshan decided to use Arecibo to search the sky overhead for pulsars. You might remember pulsars. These were our rotating neutron stars first discovered by Jocelyn Bell, emitting both bright and perfectly regular pulses of radio light like a finely tuned ticking clock. However, one of the pulsars found at Arecibo that night wasn't quite right. Its clock appeared to be stuttering, speeding up and then slowing down at regular intervals. The variations were small, only a few milliseconds, but pulsars are supposed to be perfect. This pulsar was skewed like something was nudging it back and forth in the sky. At the time, Wolfshan was a published expert on the timing of millisecond speed pulsars. He had grown up in Szolnocz in Poland with an early interest in astronomy, encouraged by stories from his father that were based on the myths of the constellations. After getting his PhD at auspiciously Nicholas Copernicus University, Wolfshan eventually moved to the United States. When he discovered this strange pulsar at Arecibo, he suspected right away that the effect could be coming from a planet around the pulsar, but there were a few problems. To begin, we need to look again at how we think planets are formed. Planets are born at roughly the same time as stars, coalescing out of the dense disks of gas and dust left around stars near the beginning of their lives. You might remember that pulsars are formed in the supernova deaths of massive stars nearing the ends of their lives. But stars massive enough to die as supernova aren't expected to successfully form planets, mostly because in their early lives they get so hot that planet formation in these disks becomes very difficult. And if the planets did manage to form, the violent supernova death of the star itself would likely obliterate them. Planet formation around pulsars isn't impossible, but it is unlikely. Today we think that planets like this would form if the pulsar used to have a companion star that was destroyed during the supernova, leaving behind leftover stellar material that could eventually form a disk around the pulsar. This disk could then accrete to form planets. They might be strange planets, born long after their original sun had died, but they're planets all the same, orbiting and tugging on the pulsar. The strange home for an exoplanet wasn't the only problem. Alex Wolfshan also knew that there could be other explanations for the velocity shifts he was seeing with the pulsar. He wasn't able to perfectly measure the position of the star with Arecibo, and he knew that if the estimate was slightly off, he might mistake the motion of a pulsar for the relative motion of the Earth. Wolfshan contacted a colleague, Dale Frail, to observe the same pulsar with the Very Large Array in New Mexico. The two began working together to carefully calculate the pulsar's position and model possible explanations for its unusual motion. By 1991 they had a proposed answer. Their wobbling pulsar was behaving strangely because it might be orbited not by one, but by two planets. It took Walsham and Frail 2 more years to confirm that the planets were there, and a couple of years later they discovered a third planet around the same pulsar. In one foul swoop they had discovered the first extrasolar planets, the first multi-planet system, and the first evidence of planets forming around pulsars. The discovery was incredible and officially launched the field of exoplanet research, but planet researchers at the time were left with something of a conundrum. This extremely unlikely planetary system had been found first, but what about planetary systems a bit more like ours? What about planets orbiting stars like our Sun? That discovery, it turned out, was just a couple more years down the road. In the autumn of 1994, astronomers Michael Mayer and Didier Queloz were observing a set of bright Sun-like stars in Haute-Provence Observatory in France, specifically searching for any evidence of planets orbiting these stars. They were using one of the methods we just discussed, observing a spectrum of each star over and over again to try and spot the telltale red or blue shift in light caused by a nearby planet. Mayer was a professor at the University of Geneva in Switzerland, and Queloz was his student. Together they designed a brand new spectrograph with the specific aim of spotting small planets around Sun-like stars. Combining a star as small as our Sun with a small planet meant that any corresponding orbital shifts in the star's spectrum would also be small. This meant that to spot it they would need an incredibly sensitive spectrograph, capable of splitting a star's light very finely into different wavelengths so that they could spot even a tiny redward or blueward shift. Almost as soon as they started using their new spectrograph, they spotted shifts in a star named 51 Pegasi, or 51 Peg for short. The 51 Peg seemed to rock towards the Earth and then away from it again, over and over, completing one cycle every 4 days. This suggested a nearby planet was orbiting 51 Peg once every 4 days, which immediately struck Mayer and Queloz as odd. They knew from the size of the spectral shift that the planet causing it must be pretty massive, but the timing of the shift told them that the planet must be shockingly close to the star. The data was telling them they had found a star like the Sun with a planet bigger than Saturn following an orbit far closer than Mercury's. At the time, most astronomers believed that such a system couldn't exist. They saw a clear difference between the small rocky planets close to the Sun, like Mercury, Venus, Earth and Mars, and the larger gas giants like Jupiter, Saturn, Uranus and Neptune orbiting at greater distances. Theory had traditionally suggested that large gas giants should only be able to form further out in their planetary systems, where both rocks and ice could be used as building blocks. The planet like the one apparently orbiting 51 Peg was referred to as a hot Jupiter, too massive to form without using ice as an ingredient, but too close to its hot host star to be in a region where ice could exist. Finding such a massive planet in such a small orbit seemed it had to be a mistake. However, other groups soon also observed evidence of the planet, and Mayer and Queloz carefully tested and ruled out alternative hypotheses. The planet around 51 Peg was real and soon nicknamed 51 Peg b, following the convention of naming exoplanets after their host stars with a lowercase letter indicating the order of their discovery. The B marks this as the first exoplanet discovered around 51 Peg. If others were discovered, they would be designated as 51 Peg C, D, and so on, but so far 51 Peg B is the only exoplanet we've found in this system. Today we think that 51 Peg B must have formed far away from its host star, and then migrated inwards, spiralling towards the star in a decaying orbit that ultimately brought it much closer to the centre of the planetary system than it had been at birth. The discovery marked the first observations of an exoplanet around a sun like our star, hailed as a groundbreaking achievement and valuable evidence of planetary systems like our own waiting to be discovered elsewhere in the universe. Mayer and Kulos ultimately shared the 2019 Nobel Prize in Physics for the discovery, and in the immediate aftermath of their 1995 publication announcing their discovery, the study of exoplanets exploded. The 51 Peg B and the 3 planets orbiting Schwarzschild and Frey's pulsar comprise the first handful of exoplanets to be discovered. Today, astronomers can count and study thousands of planets orbiting other stars, building a detailed exoplanet library that's rapidly expanding our understanding of how planets form and evolve, and just how many are still waiting to be discovered. Think back one more time to the different detection methods we discussed for finding exoplanets. Today we use all of these methods to study exoplanets, including finding planets through transits, using gravitational lensing and capturing the actual picture of one. The transit method received a giant boost when the Kepler Space Telescope was launched by NASA in March 2009. Named for Johannes Kepler, the famous astronomer who untangled the mathematics of planetary orbits, the telescope had a single straightforward goal. It was designed to continuously monitor the brightness of stars in our local Milky Way neighbourhood. From those data, astronomers could search for any telltale periodic drops in brightness from these stars and possibly reveal the presence of an exoplanet. This method of detecting planets based on transits proved to be immensely successful, purely thanks to its efficiency. Instead of studying the motion of a single star or the ticking of a single pulsar, the Kepler Space Telescope could stare at 150,000 stars simultaneously, quickly and efficiently building up an enormous library of stellar light curves for astronomers to analyze. Kepler ultimately detected more than 2,500 exoplanets, and most exoplanets we know of today have been discovered using the transit method. While it seems a more difficult approach, gravitational lensing has also been successfully used to detect planets. The optical gravitational lensing experiment, or OGLE, began in 1992 and used small ground-based telescopes to monitor hundreds of millions of stars in the centre of the Milky Way and the nearby Magellanic Clouds, specifically focusing on distant crowded star fields to maximize the odds of spotting a microlensing event from a foreground star or planet system. OGLE succeeded in 2004 detecting a planet 1.5 times as massive as Jupiter orbiting a small orange star a bit cooler than our own Sun. Finally, astronomers have successfully captured actual images of planets orbiting other stars. The most spectacular example might be the star HR 8799, orbited by 4 planets. Using one of the Keck 10-meter telescopes in Hawaii, astronomers were able to observe all 4 of these planets repeatedly over 7 years, combining the observations into an incredible animation. In it you can see the shifting twinkling of the star's light as it passes through our atmosphere, mostly blocked by the black central circle of a coronagraph. The 4 bright spots circling the star are the system's planets. The speedy innermost planet is a little closer to the star than Uranus is to the Sun. A faint slow-moving star is tracing an orbit far bigger than Pluto's. As we watch, we see an entire new planetary system orbiting a star not unlike our own Sun. This stunning clarity is a sight that once used to solely belong to the imaginations of science fiction writers and movie makers, and an incredible accomplishment of modern telescopes. The HR8799 system is just one example of the many weird new planetary worlds we have explored. Kepler-16 is a binary star system with a Saturn-sized planet orbiting both stars. A view from that planet might give you a real-life example of the famous binary sunset seen from Tatooine in the movie Star Wars. Even our closest stellar neighbour besides the Sun, Proxima Centauri, is orbited by a planet, one just 20% more massive than our own Earth. Proxima Centauri is only 4 light-years away. The odds of a star that nearby with its own Earth-sized planet seemed almost too good to be true, yet there it is. We've also still only searched a tiny fraction of the potential exoplanet host stars. This begs the question, just how common are exoplanets? Detecting exoplanets around other stars has gone from a science fiction pipe dream to an everyday occurrence in astronomy. There are several compelling reasons to continue studying exoplanets in the hopes of understanding exactly how common they are, and exactly where they are. Some of these planets occupy what we call the habitable zone, a region we will be discussing in our next program, where planets could, based on their distance from their host stars, be hospitable to life. So, what does that mean for how we search for exoplanets and how we study them? Next we'll explore how we study the environments of distant planets, how we can determine whether these distant worlds are harbouring life, and what or who might be living on them. Once again, time has caught up with us, and it's time for me to move over and make room for somebody else. We are also coming to the end of this series of shows. There are 2 more episodes left on Standing on the Shoulders of Giants, so make sure you're here next week for the next instalment. I'll see you then. Bye for now.